Dominoes. I don't think I've ever met someone who actually knows how to legitimately play with dominoes. I'm pretty sure it has something to do with matching the dots together or something. I don't know. But anyway, when most people think of dominoes, they probably imagine a domino run. You know, where you stand them up in a line so they can knock each other over. I think this is how most people played with dominoes in their childhood, myself included. And recently, I went through a random phase of rewatching a bunch of old domino-related videos from years ago, which really got me in the mood to play with them again. But just as I was getting my hopes up, I quickly remembered the two things that I think we all hate about dominoes. One, you have to stand them back up after every time they fall. And two, physics is unpredictable, so a domino might not fall in the way you imagined and ruin the whole chain reaction. And I really wasn't in the mood to deal with these things. Alright, here's the goal. Make a game that simulates building and knocking over dominoes. Create a way to easily reset the simulation as many times as you want. And finally, make the simulation deterministic, so that it's easy to control and predict how dominoes will fall. The first 2 points are relatively simple. The third one is where things get a little tricky, so let's focus on that. Now, how can we make sure that our dominoes fall consistently? To help you understand my approach, let me first introduce you to Cellular Automata. In case you don't know, a cellular automaton is a simulation that runs on a grid of cells, where each cell can be in one of several possible states. And with each step of the simulation, the cells update their states based on a set of rules. For example, this is Conway's Game of Life, which is probably the most iconic cellular automaton. In the Game of Life, each cell can be in one of two states, alive or dead. There are only two rules that describe how cells behave. 1. If a cell is alive and has 2 or 3 neighbors that are also alive, then it will stay alive. Otherwise, it will die. And 2. If a cell is dead and has exactly 3 living neighbors, then it will become alive. Otherwise, it will stay dead. Despite the simplicity of its rules, the Game of Life is capable of some truly incredible things. With it, people have created elegant patterns, programmable computers, and even the Game of Life itself. This is a defining characteristic of most cellular automata. Complexity emerges from simple rules. And as you'll see, this will really benefit our domino simulation. So let's get back to that. First things first, let's figure out the set of states that we need. What states can a domino be in? Well, it can be standing, which of course means that it's still upright. It can also be fallen, where it's laying flat on the ground. And finally, we'll add an intermediate state called falling, where the domino has just been pushed and is actively falling over. Okay, we have our 3 states. Now this next step is uncommon in cellular automata, but along with a state, each domino also has a rotation that we need to keep in mind. This matters to us because the direction a domino is facing affects the manner in which it falls, as well as how it affects the dominoes around it. We're going to use a 2-dimensional square grid for our simulation field, so we'll allow dominoes to be rotated in one of 4 directions, either up, down, left, or right. Next, we need some rules. Since our goal is to make a domino simulation, we need rules that will cause dominoes to knock each other over, as they do in real life. Let's go through each state and think about what kind of rules a domino should follow when it's in that state. So first up, here's a line of standing dominoes. I think it's pretty self-explanatory that if a domino is only standing still, it'll never do or affect anything on its own. Because of this, we actually don't even need any rules for them. We can simply let them be. We have a similar case with fallen dominoes. A domino that's laying flat on the ground has no way of doing anything, so the fallen state doesn't need any rules either. Finally, let's look at falling dominoes, which are not as easy as the others. I'll stand these dominoes back up, and I'll also knock over this one by changing its state to falling. So what happens now? Well, if you think about it, this falling domino will do 2 things in the next simulation step. It'll push the domino in front of it, and it'll fall down itself. Let's make some rules to reflect this behavior. The latter is simple. A falling domino will always become a fallen domino. Easy enough. The next rule is a little trickier. If a falling domino has a standing domino in front of it, then the standing domino will face the same direction as the falling domino, and then become a falling domino. Let's step through the simulation to see how this works. Here's the first step. Notice how the second domino is now falling in the same direction as the first, and the first domino is now fallen. In the next step, the same scenario occurs with the second and third dominoes. The third becomes falling and faces the same direction as the second, and the second becomes fallen. If we let the simulation play, you can see that the effect continues to propagate down the line. Also, notice how we've specified that only standing dominoes can be knocked over. This makes sense. If a domino has already committed to falling, then there's no way we can change that or affect it any further. And with that, there we go. We've made a working domino simulation with Cellular Automata. Well, kind of. Okay, before we continue, let me just clear something up. Even though our simulation does take heavy inspiration from Cellular Automata, I don't think it's necessarily correct to call it one. If we look back at the rules of Conway's Game of Life, notice how they imply that a cell should only look at its neighbors and then update itself independently. This is a major characteristic of the vast majority of Cellular Automata. But in our simulation, a falling domino checks the domino in front of it and directly updates its state to knock it over. Now, this does make a lot more sense than if the standing domino looked at the falling one and knocked itself over. But the fact that our dominoes do this means that they don't truly behave like a cellular automaton. And that's not bad. I mean, that's fine, it's not going to be a problem, but I just wanted to make that clear. Okay, now that we've defined the rules of the simulation, we can finally get to the fun part. Remember what I said earlier, complexity emerges from simple rules. So let's explore this a little and see what kind of cool stuff we can do. Here's a line of dominoes where both ends are in the falling state and also facing towards each other. Logically, if two waves of dominoes run into each other head-on, they should collide and stop. And this is exactly what happens here. Since our rules state that only standing dominoes can be knocked over, the waves stop propagating as soon as there are no standing dominoes left. Here we have two lines of dominoes that intersect one another. What do you think will happen if we knock over both of these lines at the same time? The vertical line is shorter, so this wave will reach the intersection first. Now remember that falling dominoes knock over other dominoes in the same direction as themselves. So the domino at the intersection will fall upwards without affecting the others on its sides. Now the horizontal wave reaches the intersection, but since the domino has already fallen, it stops short, and the dominoes on the right remain standing. We just use one line of dominoes to block another. Pretty cool, right? And keep in mind that we never actually wrote any specific rules for this behavior. They're just the natural consequences of the rules we've already defined. So are we done? Well, not quite yet. There are still a few important things our simulation can't do. For example, what if we wanted a line to turn 90 degrees? Right now, our dominoes only fall in straight lines, so this is impossible. What we need is a new kind of domino that's angled to knock over dominoes on its side. And so I present to you the diagonal domino. This domino follows all the rules that we've already mentioned, but with one key difference. When it falls, instead of just knocking over the domino in front of it, it also knocks over the one to its left or right, depending on which way it's oriented. This domino now lets us split, merge, and rotate lines in any direction we want. Pretty useful stuff. At this point, our simulation is pretty much fully functional, but just for the sake of convenience, I'm going to quickly introduce a few more useful components. First up is the fork domino. As the name suggests, this domino acts like a fork in a line. It can split a line into two, or it can merge two lines together. Up next is the trigger. This component simply triggers the domino in front of it to fall at the start of the simulation. That way we can, actually make the dominoes fall. And finally, this is a crossover. This allows two lines of dominoes to cross without interfering with one another, kind of like a bridge. The wave goes through the crossover and then out from the opposite side. I can imagine this thing being particularly useful. And that's pretty much all of the simulation features I've created, so without further ado, let me show you what the final result looks like. So here we are in the game. As you can see, we have buttons that let us select, place, rotate, and delete objects. In the bottom left corner, there are buttons to play, pause, step, and reset the simulation. At the top is a slider which lets us control how fast the simulation runs in ticks per second. And finally, in the bottom right corner, there are 2 buttons for saving and loading what you've built. When you click save, the save data is copied to your clipboard, which you can then store by pasting it somewhere else, like a text file. Later on, you can click load, which reads the data from your clipboard and loads it back into the simulation. Overall, I find this game pretty fun and easy to use. I will admit that it does lack editing features at the moment, but if this video becomes popular enough, I'd be more than happy to update it and add more features. If anyone wants to try it out for themselves, I'll post it on itch shortly after uploading this video. The link to my itch is on my channel page, and I'll also put it in the description in case you feel particularly lazy today. Alright, so the simulation is great and all, but making it would be kind of pointless if I didn't put it to good use. So what am I going to do with it? Well, remember how I said earlier that I rewatched a bunch of old Domino videos? I came across a particularly interesting one that I vaguely remember from a while back, created by the channel Stand Up Maths, the 10,000 Domino computer. In this video, a team spends an entire day building a massive domino run that has the ability to add 2 numbers together and output their sum. They also explain a lot about the internal logic of the computer, as well as the many fears and challenges they faced. Being the lover of computers that I am, this video got me hooked really quickly, and I found the concept very intriguing. But after some digging online, I found surprisingly little information on Domino computers, which I think is really odd considering how popular the original video is. Because of this, I thought it'd be cool if I used the Domino simulation to explore this untapped field of domino computing, and hopefully dive into it a lot deeper than anything I found online. And of course, I'll definitely share the things I've discovered on this channel. Who knows, maybe this will turn into a fun little video series. Let me know what you think about this in the comments, and if you're interested, also be sure to like and subscribe so you won't miss out on future videos. Also feel free to check out my Discord server, where you can message me, hang out with others, and share your great ideas. And with that, thank you so much for watching, and I'll see you next time.